So we'll start right away with solving the second order differential equation using Matlab. This is our problem statement. We have a second order differential equation d2y by dt square plus dy by dt plus 5y equal to 5e to the power minus 5t. These are the initial conditions which are given. Y at 0 is 1 and dy by dt at 0 is 0. It is asked to solve this differential equation using Euler's one-step method. So before moving on to the solution, just a brief info about Euler's method. Yeah. So let's suppose we have this particular curve y, which is the solution of the differential equation. We have the time steps on x-axis and the value of y on y-axis. So what Euler's method does is that obviously it is a numerical method, so it works in iterations. So in each iteration it will compute the value of y using the previous value of y as well as the slope at that particular point. So we have the initial conditions with us. At 0 we know the value of y and the slope of y, so and the slope of the curve. So at this particular point, suppose this is the beginning where we know the initial conditions, we know the value of y as well as the slope at this particular point. So using that slope for the for this particular step, so in numerical methods we have something known as steps. So from xn to xn plus 1 is one step, from xn plus 1 to xn plus 2 is another step. So for each step the slope is assumed constant here. We know the value of y, we know the slope between xn and xn plus 1, so we can compute the next value of y at xn plus 1. Once we have this value of y at xn plus 1, we can compute this new slope, and then using that slope we move forward again. So that is what Euler's method does. If anyone needs additional information on this method, I'll leave a link in the description, and also the link will be available on the top right corner of the screen. So you can refer that video if you want to know more about Euler's method. So here we'll start with our solution. So let's define the step size first. Step size is generally defined by h, so let's assume h is 0.1 in our case. So in the curve that we saw, if we have smaller step sizes, then this curve would the approximated curve would strongly mimic the actual curve. So it is good to have smaller step sizes, but then again it increases the computation time, so you need to have a trade-off between the two. So yeah, we have the step size defined, then we'll define the fixed time instance. So let's suppose the simulation starts at t equal to 0, and we should have a final time at which the simulation should end, so that it could go from t0 to t0 to tf in steps of 0.5. So tf would be, let's suppose in our case, 25 seconds. We want the simulation to run for 25 seconds. We have these defined. Then let us move to defining initial conditions of the differential equation. So we know that the value of y, we'll close this, we know that the value of y at 0th instant is, or at t equal to 0, is 1. So we'll have y equal to 1 here. Next we know the slope of y at t equal to 0 is 0 from this initial condition. So I'll follow a notation here where I'll denote dy by dt as y1. So y1 is 0. I'll also mention that in the comments. So I'm assuming that y1 is dy by dt, and y2 similarly will be dy1 by dt or d2y by dt square. So these are the initial conditions that we have. So as the algorithm moves forward, we'll have the solution, that is y, the value of y will obtain at each iteration. So we'll store those solution variables, solution values of y in an array. So let's keep that array empty here, and we'll also have a time array which will keep empty for now and later populate it with time instance for which the iteration is running, so that we can finally plot the value of y with respect to time. So okay, so here all the initializations are done. Now since Euler's method is a iterative algorithm, we'll have a for loop here. Let's suppose the iterative variable I'm choosing as I, so I should run from initial time in steps of h to tf. So it will run from 0 to 25 seconds with an interval of 0.1. It's obvious that it will take I think 250 plus 1, that is the 0th time, so 251 time instance. Sorry, just there won't be a semicolon here. Now we'll need the differential equation that we have with us. So d2y by dt square plus dy by dt plus 5y equal to 5e to the power minus 5t. So yeah, we'll have y2, that is d2y by dt square. If I keep this term to the left hand side and shift all others to the right, we'll get y2 equal to minus y1 plus 5y, sorry, minus y1 minus 5y plus 5e to the power minus 5t. So this will be minus y1 plus 5 times y, sorry, again I'm writing plus, this should be minus, plus 5 into e to the power minus 5 into, sorry, t. So t in our case is the iteration variable I. It is denoting the time at each step, or it is denoting the time step. So it should be 5i. So we have the differential equation ready with us here. Next we'll write the update equations for y as well as dy by dt. So as per Euler's method, the new value of y will be the old value of y plus the step size times the rate of change of y. The rate of change of y is nothing but dy by dt, which in our case we have denoted using y1. So it will be y equal to y plus h into y1. This will give us the new updated value of y. Similarly, we can update the value of y1 in each iteration. So y1 will be equal to the old value of y1 plus the step size into the rate of change of y1. Now y1 itself is the rate of change of y, which is dy by dt. So the rate of change of y1 will be d2y by dt square, or y2 in our case as we have defined here. So it will be h times y2. So we have the update equations ready with us, as well as the differential equation defined here. So next, when we obtain the value of y here in each iteration, this should be stored in an array which we previously defined as y final, being an empty array. We'll populate it using the values of y obtained in each iteration. So y final will be y final appended with y, and then t final will be the empty array t final, which is empty in the starting, appended with each time step, which is taken care of by I in our case. So at each iteration, the value of this particular I, or the step value, will be stored in t final, which will help us later to plot it. Here we end our iterative algorithm, and then we can have a plot. On our x-axis we have t final, whereas on y-axis we have y final. So this is the plot that we'll obtain. Let's try running this. I think it has come here. Okay, so this is the plot of y that we have obtained. So we can check at the beginning. So the initial condition was the value of y at t equal to 0 was 1. So in the plot also we can verify that at t equal to 0 the value of y is 1, and the slope at t equal to 0 was 0. So it's not quite evident here, but if we zoom in a lot, then we can see that at t equal to 0, the curve of y should have a flat start, that is its slope should be 0. And as it progresses ahead, it has some oscillations because of course it is a second order system, but these oscillations damp out after some time and then it reaches a steady state value. So the simulation has run for 25 seconds. So this is how we can solve the differential equation using MATLAB scripts. Now we'll see that how this can be done using simulation in Simulink. Now we move on to the simulation part, where we'll try to solve this second order differential equation using simulation, using Simulink. We have these initial conditions with us, and then we'll compare the plot obtained for y with that which we obtained via scripting. So yeah, we have this particular second order equation. So if we want to make a model for simulation, the best way to implement this differential equation is to keep the highest order term on one side and rest all terms on the other side. So we'll keep d2y by dt square on the left hand side and shift all other terms to the right hand side. So since there is a second order term involved, we'll first of all need integrators in our model. So we have one integrator, and then we copy this, we have a second integrator, we'll connect them. So here we are getting y, so we will connect a scope over here. So we have a scope here, we'll connect this. So the final output that we'll be getting is y, and before the integration it will be dy by dt, because dy by dt when integrated will give us y. Similarly here it will be d2y by dt square. Now let's look at our equation. So d2y by dt square is equal to minus dy by dt minus 5y plus 5e to the power minus 5t. So this signal and plus 5e to the power minus 5t should be added to give d2y by dt square. So we'll definitely need a sum block. So we have the sum, and we'll need 3 inputs. We need 2 minus signs and 1 plus signs. So the final output will be d2y by dt square. We'll write it here. One signal is coming from here, minus dy by dt, and one is minus 5y, and so this is y, and we need a gain block in between. So we have the gain block over here. The gain value should be 5. Okay, so this will give 5y, and this is a minus sign, so it will be minus 5y and minus dy by dt, and we need plus 5e to the power minus 5t. So the time we can obtain from this t is actually the simulation time, so we can get it from clock. Okay, so here we have the clock block ready with us. This will give us t, so we need to raise it to the power of minus e to the power minus 5t. So we'll need an exponent block. So we have a matrix exponential. We'll bring this. If you go into the description, it computes the matrix exponential using a scaling and squaring algorithm with a paid approximation. Matrix must be square. So we don't have a problem here, because we anyway have a singular element t, and that can be considered as 1 cross 1 matrix. So we'll connect this with t. So this gives us e to the power t, but we need e to the power minus 5t. So in between these two there should be a gain block of minus 5. So copy it from here, change the value to minus 5 and put it in between. So this gives t, and here the value becomes minus 5t, and after this it becomes e to the power minus 5t, and we'll connect this here. So this is giving out e to the power minus 5t. Okay, so we have d2y by dt square is equal to minus dy by dt minus 5y plus e to the power minus 5t, and that is exactly what we need. Now we are left with the initial conditions. So the initial condition for y at t equal to 0 is 1. So y is obtained as an output from this integrator. So inside the properties we have the initial condition defined as 0, but we need 1, so we'll change it to 1. Similarly, for dy by dt, the initial condition at t equal to 0 is 0. So dy by dt is an output of this integrator. We'll go in the properties, it's already 0, so that's fine. Now we wanted a simulation to run for 25 seconds as we did during scripting. So we'll change this stop time to 25. So we have got e to the power minus 5t coming out of this exponential block. But if we look at the question, we need 5 into e to the power minus 5t. So we'll add a gain block here also with gain value equal to 5. So the signal that we are getting after this is 5 times this value. So this is the final signal that we want from here, 5e to the power minus 5t. So d2y by dt square will be equal to 5e to the power minus 5t minus dy by dt minus 5y. So here our modeling is complete. Next we'll look into, so we will now look into the solver settings that we need to configure. While doing the scripting, we took the step size to be 0.1. So here also we'll have to define which method we want to implement for solving this differential equation, as well as what should be the step size. We'll take it same as the one we took while writing the script. So for changing the solver settings, we go to modeling, and inside this we have model settings. So here we can configure our solvers. We have two different types of solver selections available. One is variable step and one is fixed step. We'll choose fixed step because we want to have a fixed step of 0.1 between any two intervals. Next we'll go to solver where we'll select ODE1, which is for Euler from this drop down, and then in the solver details the fixed step size will define as 0.1, the same we chose for while doing the scripting. So the model settings and the solver has been configured. Now we'll try running the simulation to see what kind of curve we get for y. The stop time is set as 25 seconds, so we'll run this. So the simulation is complete now. We can observe the results in the scope. So this is the curve that we have got for the solution of y. We We can compare it with the previous plot. So as we can see, both plots are exactly identical. We have the initial point as 1, and then there is an undershoot which goes beyond minus 0.6, and since of course it is a second order system, there will be some oscillations at the starting which gets damped out at the end, and then we see that the final value of y settles down to a steady state value of 0. So hence we see that both the methods yield exactly the same solution for y, and therefore we can say that our result is validated when we compare the two results. So yeah, that's all for the video. I hope you enjoyed it. Thank you for watching.